All right, let's dive right in. We're going to shrink down, way, way down to the atomic level. We're on a mission to follow the journey of one tiny particle that, believe it or not, makes our entire modern world tick.
I mean, think about it. You flip a switch and boom, light. It feels instantaneous, almost like magic. But what's actually happening inside those wires? There's this incredible, invisible drama playing out at lightning speed. So, what's the secret?
Well, to get to the bottom of it, we have to meet the hero of our story, the main character, the one doing all the real work. And that is the tiny but oh so mighty electron.
Okay, so full disclosure here. Real deal modern physics gets complicated. It talks about electrons living in this fuzzy probability cloud. But for our purposes, to really get a grip on how electricity works, we're going to use this much simpler picture, the Bohr model. It's kind of like using a simple map instead of a super detailed satellite image. It shows us everything we need to see for the journey ahead.
So here's the absolute bottom line, the one thing you really need to remember. An electron has a negative charge, and when it moves, that movement is electricity. Seriously, that's it. The whole big mystery of electricity, it's just a whole bunch of these little guys all deciding to go for a jog at the same time.
But the scale of this, oh man, it's just wild. The charge of a single electron is, well, look at that number. It's measured in something called coulombs, but honestly, it's so ridiculously tiny it's almost meaningless on its own. It's like trying to imagine a single grain of sand on all the beaches in the world.
So to put that tiny number into perspective, let's flip it around. To get just one single coulomb of charge, which is a basic unit we use in electronics, you need, wait for it, about 6.242 quintillion electrons all bundled together. That's a 6 with 18 zeros after it. It's not one electron that matters, it's the sheer power of their numbers, this massive team effort that actually powers our lives. Okay, so we've met our hero, the electron. And we know they're team players, they have to move in these gigantic groups. But how do they get from point A to point B? What do they travel on? Well, like any good road trip, they need a highway.
And there's a name for this movement, of course. We call it electric current. Think of it like a river. It's not just that the water is moving, it's about how much water is flowing past you every second. Same idea here. It's all about the rate of flow.
But here's the thing, not all materials are created equal. Some are superhighways for electrons, and some are just, well, they're dead ends. The highways are called conductors. Think of metals like copper. Their atoms are set up in a way that creates this kind of sea of free electrons that are just itching to move. Then you have insulators like rubber. Their electrons are locked down tight. They're not going anywhere. This makes them great roadblocks, which is, super important for safety.
And yeah, we can totally measure this flow. It's pretty straightforward, actually. You start with a big group of electrons, that's your charge, or Q, then you watch them flow past a single point, and you time it. The rate you get, how much charge flows in that amount of time, that's your current, which we call I. And this gives us the unit we've all heard of, the amp, or amp. So when you hear 1 amp, what it literally means is that 1 coulomb of charge, remember that 6 quintillion electrons, is zooming past a single point every single second.
Wow. Okay, you ready for a fun fact? Something a little weird? It turns out that for a very long time, we've basically been drawing our maps of electricity upside down. We've been thinking about it backwards.
So here's the deal. We know for a fact that electrons are negatively charged, right? So naturally, they're going to run away from the negative end of a battery and race towards the positive end. Makes sense, negative to positive. But way back in the day, before we even knew what an electron was, thinkers like Ben Franklin had to take a guess. And they guessed wrong. They figured the flow went from positive to negative. We call that old idea conventional current. And just to keep things interesting, it's still the way we draw it in almost every single circuit diagram today.
It's just one of those weird things, a total quirk of history. The rules were written before we had all the facts. And even though we now know what's really going on inside the wire, the old convention just stuck. So if you ever see a diagram where the current flows from positive to negative, don't worry, you're not going crazy. That's just us honoring a very old and technically incorrect tradition.
All right, so we've been deep in the weeds, following this tiny electron on its slightly confusing, kind of backwards journey. But let's zoom out. Why should you care about any of this? Well, let's look at the absolutely massive impact this little particle has on, well, everything.
Think about it. The light bulb of your head, the phone that's probably in your hand right now, the device you're watching this on, even entire cities. Every last one of them is powered by the very same thing we've been talking about. Trillions and trillions of electrons all moving together through a wire. It all comes back to that one simple controlled journey.
So, the next time you flip a light switch, just take a second. Remember that invisible river of electrons you just unleashed, flowing through the walls? A single electron's journey? It's basically nothing. But get enough of them together, and their combined strength has literally built the world we live in. And it really makes you wonder, doesn't it? What are they going to power for us next?